Hello everyone, this is the April 22nd Organic Chemistry 2 lecture, and in this lecture we're going to start talking about carbohydrates. Hopefully by this point you'll have received an email from me telling you that Monday's lecture was the last material before the exam. So if you've received it, great. If you haven't, take a look at your email because there's a message in there and I'll tell you which chapters the exam is going to be on. This is exam 4 I'm talking about. So chapter 24 is carbohydrates. They receive their name from their apparently simple structure, that is CH232. So the molecular formula is based upon the number of carbons equaling apparently the number of water molecules in them. So carbohydrates make up the largest part of our diet. For example, if you place a piece of bread in your mouth, a short while later you'll find that you're starting to get a sweet taste in your mouth. This is enzymes in your saliva that are beginning to break down the starch into its component glucose molecules. So starch in itself doesn't taste sweet, but when we start to break down starch itself, we start getting the individual carbohydrates that we find sweet in our diet. The names and structures of carbohydrates. One sugar molecule is referred to as a monosaccharide, and if you have a whole bunch of sugar molecules that are all connected together, this becomes a polysaccharide. Okay, so there are two types of, or families of sugars. There are aldoses and ketoses. Hopefully you guys are savvy enough at this point to understand that an aldose probably involves an aldehyde, and it does. So here is the simplest aldose, that is glyceraldehyde. One could also name this 2,3-dihydroxypropanol. Generally the name that's used is glyceraldehyde. Ketoses, these are sugars that involve a ketone. Again, not too many surprising things here. The simplest ketose is 1,3-dihydroxyacetone or 1,3-dihydroxy-2-propanone or just propanone. Sugars are also categorized by the carbon chain length, which is not too surprising because carbon molecules are categorized by their carbon chain length. So 3 carbons are called a triose, 4 carbons tetraose, 5 carbons pentose, and 6 carbon hexose. And so with carbohydrates, we find that we have a bunch of sugars that all have common chain lengths, and the only difference in those molecules is the stereochemistry of different bonds. So this is part of what makes carbohydrates such a complex set of molecules, is there's all these stereocenters and there's all this potential for difference, and we start seeing a lot of different molecules in the end. So normally sugar structures are depicted as Fischer projections. So on the next page you'll see some examples of Fischer projections of sugars. At the top of the page we have R plus 2,3-dihydroxypropanol, or D plus glyceraldehyde, and its enantiomer is L minus glyceraldehyde or S minus 2,3-dihydroxypropanol. Okay, so these are the two enantiomers, and they indicate the stereochemistry at these positions. Now, before the development of the R and S system, D and L were used to indicate stereochemistry, and this is where this naming system comes from. Now, it turns out that the D and L always indicate the stereochemistry at the highest number stereocenter. So in this molecule here, which is D-aldose, the highest numbered stereocenter is the one here furthest from the carbonyl group, right here, and this is where the stereochemistry is always going to be. Now, the reason for this rests in the idea that the original designations for these sugars were based upon the oxidative cleavage reactions which formed glyceraldehydes that were used to identify these different structures, and this is why it was formed the way it is. The plus-minus designations indicate the direction in which a plane of polarized light is rotated, and this is something that's reviewed from Organic 1. Part of the complexity of these molecules comes from the number of stereocenters that that each molecule possesses. So if you remember back from stereochemistry a long time ago, but you guys should start reviewing this stuff now for the final. Remember that the number of stereoisomers equals 2 to the nth power, where n is the number of stereocenters. So for aldopentose, for example, there are 3 stereocenters. There is upwards of 8 stereoisomers possible. So due to the complexities of these molecules, what we're going to find is we're only using common names. Now, if you go down here, you'll see that the aldopentoses, or the C5 molecules, there's only 4 examples down here. Why are there only 4? Well, the answer lies in this statement here. Nature only uses the D form of the sugars. Now, this is not completely true, but for the most part, it's pretty true. And so as a result, we're basically taking one stereocenter out of the equation because it always stays the same. And so that's where the other stereocenters are switching, and this is where we get our differences in different sugars. So the aldoses, we see a triose here. This is glyceraldehyde, D plus glyceraldehyde. In the tetraoses, we have D minus erythrose, and erythrose has both hydroxyl groups on the same side. D minus threose, one hydroxyl group, still D down here, and then the other one is switched. And that's what we're going to see in all of these structures. Here for the pentoses, we see we have D minus ribose. All of the OH groups are on the same side. D minus arabinose, we have 2 on the same side and 1 on the other. Remember, the bottom one's never going to change, it's always going to stay D. D plus xylose, we have the center hydroxyl group switched over. And then last but not least, D minus lixose. I don't really know if that's how it's pronounced or not, but let's go with it. And this is the last pentose. Now we're going to have 8 hexoses to look at. So here are the hexoses. We have D plus allose. Again, all of the hydroxyl groups are on the same side. You can see that it's rather systematic how you've presented, these have been presented. D plus maltose, okay, top one is switched. D plus glucose, the second is switched. Glucose is brain sugar. D plus mannose, D plus gulose, D plus idose, D plus galactose, and D plus talose. And you can see that the stereochemistry of all of these varies in a very systematic way, but they all vary and they're all different molecules. So you can imagine the problem of identifying these individual species because of just changes in stereochemistry. Now the ketoses, the simplest is dihydroxyacetone, and it's the only carbohydrate that has no chiral centers. Then the next tetraose, D minus erythrulose, there's only one example because the only stereochemistry is D, and that's the one that doesn't change. We go to the pentoses now. There are only 2 because we've removed a stereocenter and essentially oxidizing that second position. So in this case, D plus ribulose and then D plus xylulose are the 2 pentoses in these ketoses. The remainder of the structures here, here are the hexoses. We have D plus psychose, D minus fructose, D plus sorbose, and then D minus tagatose. And again, you can see how the different hydroxyl stereocenters are changing. Now, just to go back to glucose for a short time, you also known as dextrose or blood sugar or grape sugar. In human blood, concentrations of glucose usually varies between 0.08 and 0.1%. The corresponding ketose to glucose is fructose, and also fructose is one of the sweetest natural sugars. It's present in fruits and honey. Now the interesting thing about this is that there's controversy in our society concerning the use of high fructose corn syrup. Why is industry so intent in using this? Now if you think about this, fructose is the sweetest sugar. That means that to get the same level of sweetening in products, they have to use considerably less fructose than they would glucose to get the same level of sweet flavor in the material. And this is part of the reason it's going to be very difficult to get fructose out of the system. At any rate, that is all for today's lecture. It was a quick one. Have a great day, everyone. See you next time.